Right, so Newton found out that a pull between two objects will be as the bigger the mass of each, but the smaller the bigger the distance between them, and not just distance, more precisely, and genius of him, square of the distance squared. And that is thought to be a very good mathematical insight, and that follows from the Kepler's law. Remember, there was this area of cones in there, right?
Mm-hmm.
Well, you know that areas usually have squares of something, you know, like area of a rectangle or of a square is actually the side squared, right?
Yeah.
So that what happens to the circle, the area of a circle. What is the formula for area of a circle?
It's R2 by the power of pi.
Yes.
I mean, no.
Pi r squared, yes. Now, area of an ellipse is very similar, but you gotta know how squeezed it is. You know, what is the difference between one radius and the other radius. But it also involves a square, and that where distance square comes in Newton's law. So actually, no apples or, you know, objects lying around helped him understand that. It was astronomy that helped him understand things that we now use for everyday objects, planets. So, but you gotta add a number that makes everything right. You gotta multiply by something called G, and that's not the G that you learned. It's not the 9.8 G. This one is called the universal gravitational constant, and it's a huge number. And it's just there so that, you know, because your mass is in kilograms, your distance is in meters, but you want to get some nice number for the F, right? So to get a nice number, you multiply by something Newton called a constant, a number that you gotta, you know, either memorize or look up. Let's look at the gravitational constant. So, universal gravitational constant. I'm sorry, it's not a huge number. It's actually an extremely small number.
Oh, wow.
So G equals this. And you see it has all the units we know, basically. Kilograms, seconds, meters cube. Why does it have all of this? Because you want them to go away when you multiply them by the mass, and then mass again, and then meters squared. See? Basically, let's say, what is the gravitational pull between you and your table? We're going to take your mass, probably 50 kg. Mass of your table, probably 10 kg. Divided by the distance between you, probably like 10 centimeters right now, which is 0.1 meter. Remember, meter is the international unit, right? But we've got to square it, so it's going to be 0.001. And that's meters. But you don't want to measure force in kilograms times kilograms divided by meter. That's tiring. So you multiply it by some weird number, and at the same time you multiply it by meter and divide by a kilogram, because see, kilogram minus in the power of -1, that's division by kilogram. Okay?
Okay.
And then some extra units, so all of this goes away, meter and meter go away, kilogram and kilogram go away, and so on and so on. And you're left with something that we now call newtons. What is 1 Newton? 1 Newton.
It's like force, right?
Yes, it's force, which does what? It can, it's a force which gives a mass of 1 kilogram it can move 1 kilogram accelerated to 1 meter per second. So if you take a backpack that is 1 kilo, 1 kilo, right? And you push it, and for a moment it moves at a speed of 1 meter per second, that means you just applied 1 Newton of force, 1 Newton. So in the end, Newton is also, if you decipher what Newton is, So this equals so-and-so newtons, which is actually lots of things. It's a kilogram multiplied by the meter that you moved this kilogram, and per second because you moved it in 1 second, and per second again because your acceleration went from 0 to 1 in 1 second. So all of this information is here, and now we call this a newton.
Oh, okay.
Okay. Now, why doesn't this formula look anything like the formula we use, MA or mg? Well, actually, this formula, universal formula, can be used for anything, anywhere in the universe, on the planet Earth, in cosmos. It just becomes a simpler formula if you say that the second mass is as mass of your planet Earth. Radius is radius of Earth, because what is the distance from you to the center of Earth? It's equal to the radius of Earth. Okay?
Yeah.
So radius of Earth. And to make this whole thing again look like a newtons, you add something which is the small g, which is the acceleration of free fall. If you're talking about free falling, if you're talking about cars and airplanes, then you add something else. You add acceleration. A, acceleration. And then that first formula becomes the second formula, which is F equals m times A. Force that is on the object, that the object exerts, sorry, not on the object, exerts, will be the bigger the mass, and the bigger the acceleration of the object is. And since all of the objects are more or less the same distance from the center of Earth, then we just don't care about it. We put it inside the formula. It's hidden now. Now back to Newton's law 3 paradox. Why doesn't the Earth stick to our feet? Although I have to think about your idea, which I like, inertia. Well, actually, the answer is the Earth does stick to our feet. It's just that it doesn't have enough time, and we don't have enough. Yeah, basically, we don't have enough time to watch this, because, see, let's rewrite the Newton's law 2 again. Right? And let's use it twice for you and planet Earth. Like, force of Sophie is mass of Sophie, which is around 50 kg, times acceleration of Sophie, which is acceleration you give yourself when you jump up. Acceleration of the jump.
Mm-hmm.
On the other hand, it must be equal to force of Earth, but in the opposite direction. So physicists write minus to show that it's the opposite direction. However, mass of Earth is not the same as mass of Sophie. Let's see how many times bigger, heavier the Earth is. Good thing we learned about standard form.
Yeah.
So that's basically a number with 24 zeros. So it's this many times bigger than your mass, and then multiplied by the acceleration at which Earth will be sticking to your feet. Now, will this acceleration be equal to your acceleration or not?
It won't.
Right, not, because the forces are equal.
Mm-hmm.
Mass is much smaller than the Earth mass, so that means acceleration of Earth must be much what?
Slower?
Smaller, yes, and slower than yours. So much slower. Then it's even unintelligible. It doesn't make sense to talk about it. So the acceleration at which the Earth is trying to glue to your feet is so small that we can't really talk about this realistically. You would need I don't know what kind of instruments and what kind of time to see that it got closer to you. But at the same time, theoretically speaking, you do attract Earth to your feet. And every bird, every plane, every insect. The acceleration is different. The acceleration is different. Now, of course, we know that Newton's theory was, depending on how you look at it, completely demolished or upgraded by Einstein. Because Einstein said, yeah, you know what, there is something that kind of pulls objects somewhere, but it's actually not a force between two objects anymore. So in relativity, you study that basically the heavier the object, the bigger the hole it makes in space, and things just fall into this pit. So heavier objects press, quote unquote, into space more, so objects around it fall into the pit, quote unquote. Now, philosophically speaking, that just completely destroyed what Newton said, because it's not a force between objects, it's not a force. At the same time, it's not what people think. People think it's an upgrade, because you can still use Newton's ideas to calculate almost anything. You only need Einstein's ideas if you try to land a spaceship or put a satellite in the space. That's when there's a little difference. When you need precision so big that it's something eyes cannot see, and it's something we never deal in our lives. So that's what's cool about physics and science. So people don't say Newton's ideas are wrong and stupid. They say it's one of the ways to look at reality. Einstein's is another way to look at reality. You could and should use both. So there is no final truth. First of all, we don't know if Einstein's relativity cannot be upgraded further. And second, if they both work, well, which one is the truth? There is no such thing. They're both true. And I think this finishes the little lecture. I will send you a video, or maybe a couple. One demonstrates how it's easily, how you can follow this idea that because of Kepler's laws, you have Newton's second law, and how this whole history expanded, what these guys had to go through. Lots of them were, I don't remember, where was any one of them burned at the stake by the church, or they all made it through?
What?
Well, the church burned people, right? Yeah, Newton was respected. Aristotle told me were very respected people. Well, these people were also respected. So, no, I think they all made it. Galileo was alive at the end of his life. Oh, I mean, not murdered. Kepler was with him. Brahe died of a stroke. Copernicus, I'm not sure. Let's look at Copernicus' death. Stroke. Okay, how did Brahe die then? I'm confusing the two. Kidney stone. Okay. That means they're old enough to die of some health problems. That means everything is fine. Now, who died at the stake was, what's his name? That he said that Earth is round.
Oh yeah, I think for that guy, didn't the church first try to like
dissuade him? Yes.
They held him in church and like the earth is flat. You have to do this, blah blah blah, believe in this. But he's like, no, the earth is round.
Yeah. First they tried, as they always do, to make a person go against his own words, and he didn't, and they killed him. Who said that? Megastem. And now people think that it's actually the idea is older. Brahmins of India believed in spherical Earth.
Ooh.
Okay. Okay. Burned for saying Earth is round. Giordano Bruno. Notice how he is much later. So 16th century, so it's like 15 something. And here it's already, you know, Galileo is already doing his work. No, sorry, is it which? 16th, yes. So the same time as Galileo lived, Kepler lived, and that's very interesting. So we never, and I never mentioned, I have to check this. Did these guys believe in a round Earth because their flying planes could be still flat? Did these guys believe it and were not burned? Why were they spared then? That's a good question. Okay, let's Google this. Why was Bruno burned and not others?
I think it was because the others, they didn't like say exactly like, oh, the earth is round.
Maybe.
That's how it is.
Maybe.
And at the time, people didn't really focus on like, oh, hey, if you're like thinking makes the earth round, that's not true. So
that might be one of the things that happened. Yes. Well, I'm gonna find out because I found something about comparing Galileo and Bruno. First of all, he was a pantheist. He believed in reincarnation, in many gods. Okay.
Sorry, you were cutting out.
So it says he was a pantheist first and foremost. He believed in reincarnation of souls, many gods, and so on. And he was blamed for this.
Oh, okay.
And then okay, so he read the Galileo's works and heliocentric theory, right?
Yeah.
And he tried to reinterpret the holy texts to fit in the new scientific ideas. And that's what got him in trouble.
That would definitely make sense.
Mm-hmm. He was not imprisoned, he was put under house arrest. Wait a second. Wait, was he burned or not?
Yeah, I think he was burned because, like, then said.
Oh, it was Galileo who was under house arrest. Yes, I know that. But Bruno was burned.
Mm-hmm. Yeah.
So Gleo was, it says, smart, and he agreed to recant in exchange for a lighter sentence. So he was at house arrest until the rest of his life. Wow, interesting. Bruno had many other ideas that got him in trouble. There are infinitely many worlds. Other worlds contain life. Universe is eternally pre-existent, beginning no end. Well, that's Indian philosophy. Many worlds, infinite universe. So he was imprisoned for 7 years, but he did not recant. And so they executed him. So Bruno was not exactly a researcher or scientist. He had cool ideas, and I think he traveled. Did Bruno travel to India? Not this Bruno. Yes. So he might have gotten these exotic ideas from Indians.